Welcome back. We're going to start in our calculus today. And when we talk about calculus, we normally talk about three different branches of calculus, kind of subcategories or subtopics of calculus. Those three topics are limits, derivatives, and integration. Integration is sometimes also called the antiderivative. So we'll spend the rest of this year working on limits, and then as we get into next year in AP Calculus, we'll talk about the derivatives and the integration or the integral and the antiderivative. So what is a limit? A limit is a value that a function approaches. It's not necessarily the value that the graph is or defined as, but it's what happens to the branches of a graph. So if I talk about the branches of a graph, I guess I'll put this back up here. Say we have a graph like this, and maybe we're talking about 1. So as x gets closer to 1, we know we have x values over here that are negative, and then x values over here that are positive. So maybe we have this branch, and this would be a branch, as we come into the x value of 1. So we're looking at the y values of this. And we should say that we have a nice steady slope, nice curve maybe, of y values, such that these y values are decreasing along the graph. And maybe this value here is 3. So the limit on this side of 1, this branch is getting closer to that value of 3. And maybe we have another branch coming from the right side of this graph, and maybe it comes up to this point. So here, as we get closer and closer to the x value of 1, our y values are rising so that we get closer and closer and closer here to 3. So we would say the limit of that value is 3. So the way we write that is the limit, we abbreviate as LIM. Below that, we're going to do x with an arrow as x approaches some value. So in this case, x approaches 1 of this function f of x is going to equal 3. Now you may be asking yourself, well, isn't that the actual value of the function? And in this case, it is. But what we're going to be able to do is maybe look at that hole that occurs sometimes. So maybe in this case, maybe this graph at 2, there was a hole of the graph. So maybe we look at it coming in like this, and then maybe coming from the right side, it comes up like this. So now we know that f of 1 does not exist. But we know the limit as x approaches 1, so the branches of this graph are getting closer and closer and closer to that y value of 2. It's not going to touch of 1 of f of x equals 2. So we know that it's not defined at that point, but we know the two branches now gets closer and closer to that 2 value. So now we can define, or we can describe the graph of this function a little more precisely. So we know the value doesn't exist, but the limit, so the branches are getting closer to that y value of 2 as x gets closer to 1. And what I want to do is to look at some notation as well as just talking about when a value exists and when the limit exists, or when a limit doesn't exist and a value doesn't exist possibly. So on this worksheet, we'll give you in class here. You can print one off as well if you'd like. We're going to find the limit as x approaches some values, and we're going to find the value of this function. Notice this function has a lot of things happening. All right, we have a branch coming in here. It's undefined. Then it jumps down to here. So we have a jump discontinuity. We have a solid function here, so it's defined here. Comes over, we have an open circle. So it's undefined. The graph, the two branches are coming closer to each other, but it's undefined there, but it's defined up here. So again, we have another jump discontinuity. And then we come up, and we're working our way up. We have another point that is not defined. We actually have a hole here. It's not defined, so there's no jump discontinuity. It's actually a removable discontinuity. And then if we come down here, this is going down. It's going to continue forever. But it's getting closer to this line. We call this line, remember, an asymptote. We have a vertical asymptote there. And on the other side of this asymptote, it's coming way up here. So it's starting up here, and it's coming down. So here we have an infinite discontinuity. And coming down, we have another hole, or removable discontinuity. And we're coming up here. This is going to infinity. We jump over that asymptote. We start high again, but then it comes down. And it looks like it's going off. Looks like we're getting a horizontal asymptote here to be 0. We don't necessarily know what's happening on the end of that graph. So some things that we're going to look for. One, what is f of negative 1? Well, to find f of negative 1, I come over to negative 1 on the x-axis, and I look to see where the graph is defined. Well, the graph of this is defined to be up here at 3. We have a hole at negative 2, but we have the value is at 3. Now, if I look at the limit as x approaches negative 1, that's asking what's happening with the branches of the graph close around negative 1. So this graph from the left, as x gets closer to negative 1, is nice horizontal line. And it's getting closer and closer, or staying actually, at negative 2. On the right side, this graph is coming down. Little hiccup there, little bump, and it comes down into, again, that negative 2 value. So the two branches are coming together, and it looks like if we could, they would be coming together at negative 2. So we say the limit as x approaches negative 1 is negative 2. Number 3 here, we're looking at f of 1. F of 1, here's our 1 value. Again, we're looking, well, this value is undefined. There is no value at 1 when x equals 1 there. So this value does not exist, or we can say it's undefined. But the limit as x approaches 1, so now if we take the limit, these branches are getting closer and closer and closer. It looks to what, like a 5? So the limiting value would be considered 5. On number 5, we're looking at f of 2. Here, f of 2, again, we see this, we have an asymptote. So we know that the value does not exist, or we can say that it's undefined. And the limit as x approaches 2. Well, here, on the left side, we see that this is going to negative infinity. On the positive side, we see it's going to a positive infinity. Since we know that they're not coming to the same value, the limit also does not exist. Yes, mean girls, the limit does not exist. In number 7, f of 4. So we're coming over here to 4. Again, we have a hole. So the value does not exist. But the limit as x approaches 4. Now, when I look at my branches are both coming to that same value of 1. So the limit as x approaches 4 is 1. In number 9, we're looking at f of 5. Again, if we come over to f of 5, this function, there is an asymptote, vertical asymptote, so we know it does not exist, or it's undefined. And again, it doesn't matter if we use the word does not exist or undefined. They're interchangeable for us in this case. And the limit as x approaches 5. So if I look at these two branches, I see that they're coming to the same value. They're both coming to infinity. But what do we know about infinity? Infinity is a concept. It's an idea. It's not an actual number. So what we're going to put is infinity, but we're also going to put does not exist. I like to do both of these. One, because infinity tells us that those two branches are coming to the same point. They're coming up. They're both coming up. But I also want to put it does not exist because I know infinity is not an actual value. So I'm going to be looking for both of those as we take tests, quizzes, and on assignments just so I know that you understand that they both mean the same thing. And we could interchangeably use them on a multiple choice test or quiz. Number 11, we're looking at f of negative 4. Well, here f of negative 4, we come over. F of negative 4 is defined down here. We have a hole there, but the defined value is down here at negative 2. The limit as x approaches negative 4. On the left side here, we're coming down to this hole. From the right side, we're coming over to this defined value. But the two branches, they don't seem to be coming together. So we say that the limit as x approaches negative 4, in this case, does not exist. So here we see that the value existed, but the limit did not exist. 13, f of negative 3. So f of negative 3, we see on this horizontal line again, that value is negative 2. And the limit as x approaches negative 3. So there's no big thing happening here at negative 3, but we see that it continues on this horizontal line. So I could draw a nice big old dot if we wanted. Looking at those two sides of those branches, we see that value is negative 2. And finally, we're going to examine when x equals 0. So here at f of 0, we should see that we have about negative 1. That's the value. Again, nothing big happening here. No jumps, no holes, no infinities, no asymptotes. And as I look at the value of these branches coming together from the left and the right, I see they're coming closer also to negative 1. So we should see several things happen today and on this graph. We should see where the limit is not always going to be the value, such as in the first example here at negative 1. We saw the value was up here, but the limit was down here, so the main graph branches are coming down here, my value is here. We see that we don't necessarily have to have a value of the function for the limit to exist, like in the second example, where x equals 1. So we saw that the value didn't exist, but the limit, the two branches, came closer together at that 0. We should also see where we had the asymptote and we didn't have a limiting value or a value of the function. We also saw where the two branches went to an infinity, which also is not also does not exist. And we saw where the value of the function here at f of negative 4 was actually defined, but the limit, the two branches, didn't necessarily come together. And finally, we see where we just come to a regular point on the graph, nothing big happening, where the value is actually what the limit is as well. And that's our first introduction to limits and the graphical approach of them.